I'm amazed by Vince and looking forward to what you have to say.
Thank you, Andrew. That's very kind of you. I'm amazed by you, so it's a reciprocal arrangement. Well, anyway, good morning, everyone. I'm honored to have this opportunity to be here to help celebrate Andrew, and I really appreciate the efforts of Cindy and the other organizers in putting this really delightful weekend together. So, as Andrew mentioned, he and I were colleagues at Illinois. Like Andrew, I started my career there. And like Andrew, I moved east to an Ivy League institution. So I thought, given this opportunity, I would use my time to talk a little bit about Andrew. And as he mentioned, not only did I get to know Andrew, but I got to know Gail and Roger and Andrew's family. And I'll just say a bit about that before I get started. We heard last night from Ed that Roger was a pioneer in using learning networks, and he started at Aptronics, which, despite what Marvin Minsky said about neural networks, actually made a business out of polynomial networks. And then by the time I met Roger, he had sold at Aptronics and started a new company, Barron Associates. And at that time, and I guess Gail still lives there, Roger and Gail lived on a farm outside of Charlottesville, a very beautiful piece of property. And Barron Associates at that time was basically run out of their house. So when I went there to consult, rather than having me stay in Charlottesville and drive out to Standardsville every day, they very graciously allowed me to stay in their house. So I had breakfast with them, lunch with them, dinner with them. So I got to know them very, very well. It was a great opportunity, and also got to know many of Andrew's siblings as they dropped in and out. At that time, Rowena was living nearby, and I got to see her quite a bit. So anyway, it was a bonus getting to know Andrew, but also getting to know Gail and Roger and some others of Andrew's family. So I'm not going to talk about any of my work today. This is all about Andrew, and I'm glad that he's here because he can correct any errors that I make today. But I got to know Andrew when he came to Illinois, and so I think, perhaps with the exception of Gail, of course, and his family, and maybe Ian, I've known Andrew longer than anybody else in this room, and Andrew, of course. One of the things that I did at Illinois in the early 80s, part of my service was to be on a committee that was looking at the teaching of statistics at Illinois. And in those days, statistics was part of math at Illinois. But there were still a sizable number of statisticians there, maybe 9 or 10 first-rate statisticians in the math department. And one of the things this committee talked about was whether there should be a statistics department outside of math. And I don't think this committee had any authority or power to do anything about that, but it was part of our report. And I like to think that somehow it had an impact on the administration at Illinois and wisely decided to start a statistics department. So they founded it in 1985. Like I said, there were like 9 or 10 statisticians already there. They moved out of math. And incidentally, there were also very good probabilists at Illinois at that time. Joe Doob was there, Don Burkholder, Jake Wolfowitz, and they stayed in math. So it was only purely a statistics department. The probabilists stayed in math. But anyway, they founded the department in 1985, moved to this building, Illini Hall, which is was one of the oldest buildings on Illinois campus. And started hiring people. And one of the first people they hired was Andrew. So this is how he came to be at Illinois, and this is how I came to be at this meeting today. But of course, Andrew is really an electrical engineer. He pretends to be a statistician, and he spent most of his life in statistics departments, but he's educated as an electrical engineer. And at Illinois, he also had a joint appointment in electrical engineering. It was then electrical and computer engineering. So he spent his life, at least his work life, oops, sorry about that. What did I do? I did something. Here we go. He spent his work life in these two buildings. CSL. Coordinated Science Lab. I didn't know if you were in CSL or not. Okay, so there was also the coordinated.
Very often.
Yeah.
We all had shared offices.
Yeah. Yeah, we taught in this building.
Yes, so
Yeah.
I was 75% statistics and 25%
EE.
EE, but I would spend that time
And
with you guys.
coordinated science lab. Okay, I should have put a picture of CSL up there.
Yeah.
Anyway, Everett Hall is still there, or Everett Lab is still there. It's now the bioengineering department. EE has moved out. This building, by the way, has either been demolished or is about to be demolished. So its life is going to end. So sorry about that, Andrew. So anyway, that's how I got to know Andrew. And I'll just point out something here about this number, 1985. So when Andrew arrived at Illinois, a fresh PhD, fresh assistant professor in 1985. I was already a full professor. So what's wrong with this? You're retired and I'm not. So either something's wrong with me or something's wrong with you.
Now I get to have more time for research than you do.
Yeah, well, that is, you always probably did, actually. You know, I made some bad choices in life. As you mentioned, I was a dean for a while. So anyway, so Andrew was there from 1985 to 1992. I left in 1990, so we overlapped for 5 years. And I'm going to talk a little bit about what Andrew was doing at Illinois. So that's my talk today. And the first thing I'll say about Andrew is that one thing he didn't do was get his photo taken very often when he was at Illinois. I asked everybody, when I was getting ready for this talk, I asked everybody at Illinois that I knew who might have known Andrew, including people that were overlapped with you, more recent people in the statistics department. I only got one photo out of that. I also asked Gail. Fortunately, I got some photos from Gail, one of which I'm going to use now. But you weren't really, one of your camera shy, or you're just too busy doing research, but somehow you... People were taking photos, but... Yeah, but anyway, they don't still have them. They probably just threw them away when you left, Andrew. Sorry. But anyway, I did get two. And these kind of bookend his time at Illinois. So the one on the left, that's with John, as you can see. That's right about the time he joined Illinois. So look how young he was, my gosh.
Yeah, John was born the month before
Oh, so this must have been either in Illinois or in Virginia, Illinois, yeah. And then this, Bruce Hayek was the only other person who sent me a photo. And this was taken in Budapest, actually. It's not in Urbana, but it's sort of near the end of your time in Urbana. He's giving you a certificate for having been an associate editor of the Information Theory Transactions. That's what he told me anyway. So anyway, but one thing that Andrew didn't do much of in Illinois was age. He looks pretty much the same in both photos. So anyway, but he did write some very nice papers. So this is a list of the papers that Andrew wrote while at Illinois. I'll just point out that the last two actually came out after he moved to Yale.
I did the work.
Yeah, you did the work, and I looked at the papers, and you list your affiliation as Illinois. So these are the ones where your affiliation is listed as Illinois. There were also some conference papers, which I didn't put up here. But anyway, I'm going to talk about some of these today. And I just point out, Ed mentioned last night that Andrew had written papers with Roger, and here's one of them. This was at the Interface Symposium. I don't know if that meeting still takes place, but there used to be a place for statistics and electrical engineering type signal processing to meet together. And again, just point out that, this was the early days. Roger, spent his career really doing learning networks, and then we see now how Andrew got involved, that the apple doesn't fall very far from the tree. I'll also mention that, one thing about Roger, when I was consulting for Barron Associates, sometimes I would go with Roger to visit customers or potential customers. And another thing I know about Roger, first of all, he's very good with people, which Andrew is as well. And he also had that laser focus that Ed mentioned. And when we had a mission to go visit a customer, he had something in mind that he wanted to happen, and he always kept laser focused on that. So I think in addition to your interest in neural networks, you also probably got that from Roger. Anyway, so these are the papers he wrote. Maybe there's some I missed, but I think these are most of them. And I'm going to talk about 3 of them. So there are sort of 3 themes here. One is finance. Maybe that's how you can retire before me. Another one is what we've seen a lot of today, estimation of densities and probability distributions. And I'll talk about one of those papers a little bit in somewhat detail. And then another one is a very famous paper, of course, on the approximation of single layer sigmoidal neural networks. And also, I'm going to talk about this one paper on approximation of density functions, but I'll also mention in passing 3 others. I think this one is one that Junichi just talked about. This one called minimum complexity. Or no, maybe it was, I think it was that one, minimum complexity density estimation. Okay, so why don't we get started? Unfortunately, we have Andrew here to correct all my errors. But let's talk about this paper first. So this is a paper with Tom Cover. Tom, of course, had a big interest in financial value of information. So I assume this came from some inspiration when you were at Stanford. And the question asked here is, what is the value of side information when buying stocks? So you're a hedge fund manager, and your spouse works for Google, and every evening at dinner you hear something about what's happening at Google, so you have side information you can use to improve your portfolio the next day. So this is a question that can be asked. And so here's the problem. So we have a basket of stocks, M of them, and we have daily or periodic returns that are collected in vector x. So x1, x2, and so forth are random stock vectors containing the value of the stocks over time. And we also have side information, y1, y2, and so forth, which is correlated, of course, with the value. Otherwise, it's not very useful. And then, so we're going to assume, maybe this is not a very practical assumption, but it's an assumption that's useful, that the xi and yi form an IID sequence with some joint distribution. And then a portfolio is just a vector, a probability vector, where the ith element is the proportion of wealth invested in the ith stock. So we can then write down the wealth at a given time, which is just the compounded wealth over time. And the question that Andrew and Tom addressed in this paper was how quickly can this wealth grow if we use side information to choose the investment strategy. And the result, if this thing will work, okay, this is it, folks. Let's see, I'll just move forward. Huh. Seem to be stuck, hold on. Did we do it? Let me get started again, something happened. Let's see what we can do here. Let me back out and start over. I think something jammed. Let's try that, see if that would work now. There we go, there's a solution. So the solution is set up like this. So first of all, we can define the doubling rate, which is just the maximum over all portfolios of the expected log base 2 of the value, B transpose X. So that's just the rate at which wealth doubles. And then we can define similar quantities conditioned on the side information. And then what the quantity of interest is how much the doubling rate increases due to side information. So we have doubling rate without side information and doubling rate with side information. And the main result in this paper is that that doubling rate is bounded by the mutual information between X and Y. So for example, 1 bit of side information can at most double your wealth, which sounds pretty good actually for just 1 bit. And this upper bound is achievable if you have a horse race stock market, meaning that only one security is going to win. Then this is actually an achievable bound. bound is achieved. So this is how Andrew is able to retire now, because he had side information about something, and here he is now. So the next paper I want to talk about is with Chonghua Xu. Oh, sure. Yeah. Oh, yeah, please do, actually. I was hoping you would.
This is so fun in terms of an example of the interplay of the topics. Tom first wrote this paper, and he wanted to find a clean mathematical proof, but he didn't. His proof went like this. There's the likelihood ratio test that you would have between dependence and independence of the x's and y's, and we know by the Chernoff-Stein lemma that the best exponent associated with that is IXY. And so Tom said there's also the money ratio test, or livelihood ratio test. So you compare the wealth you would have with and without that side information. And then the exponent for that is that delta W. And obviously, though the money ratio test is intriguing, it's not as good as the likelihood ratio test, and thence the inequality. But I love trying to manipulate these logs and find the right p to put in the denominator inside. And after that paper had circulated a couple of years, I found a Jensen inequality proof. Now, earlier we were wondering, does all information theory rest on Jensen's inequality? In this case, maybe it's the other way around, because I think the more fun proof is Tom's proof. So that we get the Jensen inequality of this saying that the delta W is less than I out of the understanding that you'll have a better exponent of test if you follow Neyman and Pearson than if you follow the livelihood ratio test. So I love those interconnections.
Okay, thank you. Good. Yeah, and please do elaborate. So the next one I want to talk about is an example of Andrew's work on density function estimation. And this is one with Chonghua Xu. It was one of your students, I think, right? Yeah. First student. Okay, not a bad one. So the question here is, how well can density functions be approximated by sequences of exponential families? And the basic problem is you approximate the log density with some finite dimensional family of finite dimensional space, like splines, polynomials, or trigonometric functions. And how well can you do with that? Okay, that's the question. So the problem is this. Again, we have x's, IID. These are random variables, real valued. Random variables. I'm not sure the real valued, I don't remember now. Not sure, Andrew. Yeah. And anyway, they're from some unknown probability density function. Yeah, on a bounded interval. So yes, so real valued. And then, of course, the relative entropy between the probability density and some estimate of the probability. Oh, so Pn hat is a sequence of estimators of the density, P, and the relative entropy, of course, between P, the true density, and an estimate of it is just the log integral P log P over P hat. And we want to look at the situation, as I said, where the P and hats are based on approximating the log density with sequences of polynomial spines or trigonometric series. And the question is, how does this behave for large N? And again, the solution. So with some smoothness assumptions, so assuming that the log density has R square integrable derivatives, let M be the dimension of the exponential family and N the sample size, then the main result is this, that in the case of splines and trigonometric series, if M goes to infinity such that M squared over N goes to 0, or in the case of polynomial approximation, if M goes to infinity where M cubed over N goes to 0, then the relative entropy of P to P and hat in probability is of big order 1 over M to the 2R plus M over N, okay? So this is also, the paper also goes beyond this to establish results for log density estimation based on general sequences of finite dimensional spaces. So now this has some applications back to the stock market. Andrew was focused on that, laser focused. he can, this dpp in hat, which we have now approximation for, bounds the difference between the optimal growth rate, what I defined before, delta, W, so we call it, when the investment's based on the estimated density instead of the true density. So it's a very practical result. Also, it has applications in data compression, so it determines the redundancy of the code based on the estimated density rather than the true density, and also in the development of universal codes. So it gives bounds on the redundancy of universal codes. Now, this is just one example of Andrew's work in the general area of density estimation, and I'll just mention a couple of others, one of which Junichi already mentioned. So with Bertrand Clark, he worked on this problem of approximating Bayesian density estimators. And the result there basically is a result on the divergence between the true distribution, this is a parametric problem, Bayesian, true distribution for n observations, and a smooth frequentist distribution, smooth with the Bayesian prior. And basically, the main result is that this result is asymptotically goes like d over 2, where d is the dimension of the parameter, log n over 2 pi plus some constant that depends on, this basically depends on Fisher's information at the true parameter. Another result is the one I just mentioned. This is a result on the trade-off between complexity and approximation accuracy in density estimation. This is also with Tom Cover. And in this paper, they introduced an interesting quantity called the index of resolvability of a density relative to a list of densities, so a finite number of densities, finite set, and a description length. And basically, the resolvability is this minimum that you see here. So it depends on the description. So you minimize overall densities in the list of the description length plus the relative entropy of P relative to Q, minimize that, and that's called the index of resolvability. So it's sort of the density is closest in some way in the list. And then basically the result in this paper is that the minimum complexity density estimator converges, again, in probability at the rate, this is the Hellinger distance between P and hat is, again, less than big O of this index of resolvability. And then another paper, which I don't have any equations with, is with Laszlo Jorfi and Ed Vandermeulen, which looks at the consistency of distribution estimation in terms of other measures, information theoretic measures, and total variation. So, anything, you want to add anything? No? Okay, good. Either is all wrong or all right, but either way is okay. And then I'm going to, this is probably maybe Andrew's most famous paper from that time, which is this paper on universal approximation for superpositions of sigmoids. And the question here is, how well can artificial neural networks approximate functions? And this paper has been cited 3,600 times, and of course, it continues to be cited very heavily today for obvious reasons. So here the problem is, we want to consider feed-forward neural networks, one layer, with one layer of sigmoids. So linear combinations of sigmoids where the x's, and the inputs, and the a's are d-dimensional, and then the parameters b and c are reals. And the question is, how well can an arbitrary function on RD be approximated by functions of this form? And the answer is this. So we can consider a restricted set of functions on a bounded set on RD containing the origin whose Fourier distribution is integrable and has finite mean. And look further at those such that this quantity here, which is something like a mean of the supremum, this is omega dot x, so you take the sup over x in the set B, the bounded set B, integrate that with respect to the Fourier distribution, and that has to be less than or equal to some bound C. And the punchline is that for all those functions like that, and every sigmoid, every probability measure mu, and every n, so basically everything, the square, there is a set of, there is such a combination of sigmoids. If n such that the square integral error, the integrated square error with respect to the measure mu is bounded in this way. So the integrated square error is of order 1 over n, is achieved by feed-forward networks of one layer. Okay, so this was really, to my knowledge, the first fundamental paper on neural networks that really showed that they worked. And so now we have, of course, ChatGPT, which we can blame on Andrew. So all those hallucinations and, you know, deep fakes and everything, really Andrew's fault.
Yeah. Thanks for your generous attribution. I would say George Sybinko, you may remember, was also at University of Illinois.
Yes.
And there was a lot of excitement over his universal approximation statement. It said for every epsilon, there's a network big enough that'll work. But I was looking at it going, but don't we know that because of Fourier representation theorems? And don't we also know that the classical approximation statements in terms of rate, where it would be though requiring exponentially many terms with dimension. So, but what my dad had taught me was that these things are flexible. These things can do what the traditional expansions can't. And although, you know, projection pursuit regression and other flexible statistical techniques could also. What matters is you're adapting these interior weights W. So this was the first dimension-independent rate statement for neural nets, and that's what, of course, people, you know, shocked by it, some or argue about it, and that's good. One little comment that I think is fruitful on the W norm. A lot of people just instinctively use Euclidean norms on these internal parameters. This is showing that what matters is the dual norm to whatever contains the x's. And from my experiences, x's don't tend to live in Euclidean balls. Okay? We measure variables and we measure them in a certain range, which we could make go from like -1 to 1, right? And so the appropriate norm on the W's is the dual norm on that, which is the L1 norm. And fortunately, as I've done in the work with Jason, we've learned that the statistical risk bounds that came soon after in '94, they had multiplicative factors of dimension in them. But if you really take advantage of the L1 character of what on the weights, then you can, as Jason and I and others have shown, then the dependence on dimension on the risk is just through a logarithm. So unfortunately, that message doesn't seem to go through. Although Junichi is giving us the clue, it may be okay to use L2 norms because of the nature of this spectrum of the Fisher information. But in any case, without some reason to control things, either through that spectral behavior or through an L1 control, I would not recommend training neural nets by either L2 penalties or no penalties at all, even though that is the status quo.
Okay. Anyway, thank you for all those hallucinations and deep fakes, Andrew. I really appreciate it. I'm sure everyone here can really thank you for that. Anyway, that's what Andrew did at Illinois. And I'm sure you did many other things, but that's what I'm going to talk about today. And I'll just finish by congratulating you on an extraordinarily impactful career. It all started at Illinois, or maybe it started at Stanford, but I'm going to say it all started at Illinois. I think you can see echoes of all the things Andrew's done since in some of this work. And just thank you for all you've contributed to our field.
Thanks. Vince, it's wonderful of you to focus on me, but can you just tell us a topic that you're currently working on that you're excited about?
Oh, wow. Well, I'm interested in learning also. I'm interested in federated learning. So federated learning, I don't know if people know that, but this is a type of distributed learning, a collaborative distributed learning where you have an aggregator that aggregates local models. And my main interest is in wireless networks, so my interest in federated learning is in federated learning over wireless networks. So there you have not only to worry about convergence of the learning algorithms, but you have to worry about the vagaries of the wireless channels and the resource limitations of wireless networks. So there's an interesting interplay between that and between the wireless aspects and the machine learning aspects of federated learning. So I'm very interested in that. And I'm also interested in that context, in particular in privacy issues, which is another aspect of it. If you're thinking about learning over a wireless network, you have to worry about the fact that the data being collected is private, maybe location data for people with cell phones or what have you. So that's one of the things I'm excited about now. So thank you for giving me the opportunity.
Thank you, Ben.
Thanks everyone.